Section 2 of Chapter 9, Simplifying Radical Expressions. Here we will use the product and quotient rules for radicals to simplify radical expressions. This comes directly from Chapter 5, Section 1, the product and quotient rules for simplifying like bases and their integer exponents. We also noted that for any exponent, integer, rational, or irrational, product and quotient rule for exponents applies. Here, because radical expressions can be thought of as rational exponents, that's why here we use our product and quotient rule to simplify our radical expressions. 2 says use rationalization techniques to simplify radical expressions. We will see that if we ever have a fraction whose denominator contains a radical, we will use our rationalization techniques to get that radical out from the denominator. A simplified radical expressions contain no denominator that is a radical expression. Third one here, use the Pythagorean theorem in application problems. Recall the Pythagorean theorem, a squared plus b squared equals c squared. Thus, to solve for any one of the values a, b, or c, that is, to find the length of any leg of the right triangle or the hypotenuse of the triangle, we will need to take the square root of each side of our equation to solve for a, b, or c. In section 1, we saw the result of squaring integer values. That is, if you square a negative integer or if you square a positive integer, likewise if you square 0, the result of squaring these integer values are called perfect squares. So we see that not all integers are perfect squares. We could list, for example, the first 10 or maybe even 11 perfect squares. That is 0 squared, which is 0, 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9, and continuing that list, adding 1 to the integer and squaring it. 4 squared is 16, 5 squared is 25, 6 squared is 36, and so on. Well, here we see that we're dealing with the number 48. First question here is 48 a perfect square? Well, we know that by listing our perfect squares, 36 is a perfect square and 49 is a perfect square. However, 48 is not on that list. Thus, 48 is not a perfect square. There is no integer such that when you square that integer value, you get 48. Thus, the square root of 48 is irrational. Let's think about the set of real numbers. The set of real numbers contains all possible negative and positive values and 0. But remember, some of these negative values can be irrational negative values, and some of these can be rational in that they can be written as a fraction or a whole number. So this consists of all of the numbers in the real number system. Well, dealing with square roots of values, if we take the square root of a number that is not a perfect square, then we are dealing with an irrational number. The square root of 48, whatever that is, because we know that 36 is 6 squared and 49 is 7 squared, and the square root of 48 is going to be somewhere between 6 and 7, and that value will be irrational. If you go to your calculator and put in the square root of 48, you will see it is some irrational value that's fairly close to the number 7. We would expect that because 48 is close to 49. Thus, the square root of 48 is going to be a number just a little bit less than 7, and it is irrational. It can't be written as a fraction. For these numbers that are not perfect squares, the question we want to know is, by factoring this radicand of 48, does 48 contain a factor that is, in fact, a perfect square? In other words, can you rewrite 48 as the product of 2 or more numbers such that one of those factors is a perfect square? Well, you know 48 is even. We can write it as 2 times 24. That gives us 48, but 2 times 24, neither of those factors are perfect squares. Let's go ahead and take a look as we move on. 16 times 3. Note that that is the values we're going with because 16 is in fact a perfect square. It is the result of squaring the integer 4. Now there are other integer factors here. Keep in mind 4 multiplied 12 is also 48, where 4 is a perfect square. It's the result of squaring 2, also negative 2. However, which one is the largest perfect square factor? We said 4 times 12, where 4 is the perfect square factor, but we also have 3 times 16, where 16 is the perfect square factor. So in order to simplify in that one step, we choose the largest perfect square factor of 16, and note that the square root of 16 is in fact 4. So what is the factor that's living underneath the radicand that we can simplify? Well, 16 is underneath a radical, or underneath our radical sign. What do we know about 16 under a radical sign? We know that the square root of 16 is in fact 4. Thus, we extract the factor of 4, or we factor it out from under the square root. This is known as our product rule for radicals. In other words here, if we can take the radicand 48 and rewrite it as the product of 2 numbers, where one of those numbers is a perfect square and it just so happens to be the largest perfect square, then by using our product rule, it says here that the square root of u times v is going to equal the square root of u multiply the square root of v. So the square root of 16 multiply the square root of 3 would give us the square root of 48. But we further simplify evaluating the square root of 16 to give us 4. Thus, what is the square root of 48 when simplified down? We simplify it down such that our new radicand of 3, notice what is the number now under our radical? It is 3. 3 cannot be further factored. Thus, we have a simplified radical expression. How many square roots of 3 do we have? We have 4 square roots of 3. We use our product rule for radical expressions in order to simplify our radical. Here it says let u and v be real numbers, variables, or algebraic expressions. Later we will see that our radicand will consist of polynomials. Can we factor and simplify? If the nth roots of u and v are real, the following rules are true. It says here that the nth root of u multiply v. Here we can separate the factors of u and v under the radical under their own radical sign. And this can be extended for 2 or more factors. So if we had 3 factors under the radical, then we can separate it into the product of 3 radical expressions. Likewise, for a fraction, what does it say here? As we've seen before, if we're squaring a fraction, then square the numerator and denominator. Here, if we're taking the square root, or in general, the nth root of any fraction, this is the same as taking the nth root of the numerator and dividing it by the nth root of the denominator. Now keep in mind, our denominator we do not want to equal 0. Thus, v cannot equal 0. Here we will look to simplify the following radicals by removing as many factors as possible. For parts A, B, and C, our radicands, 75, 72, and 162. Taking the square root of each of these 3 numbers. First question is, are these perfect square numbers? Are they perfect square values? In other words, can you square an integer to get 75, 72, or 162? Let's think about that. 7 squared is 49, 8 squared is 64, 9 squared is 81. So 75 and 72 are between 64 and 81. Thus, the square root of 75 and square root of 72 will be somewhere between 8 and 9. Now, 162, now 12 squared is 144, 13 squared is 169. Thus, the square root of 162 will be some number between 12 and 13. Now, what do we know about all 3 numbers for parts A, B, and C? They are irrational values. Remember, if you can take the square root of a number or fraction and you get back a number or fraction, that number that's under the radical, your radicand is considered a perfect square. Here, when you take the square root of 75, you do not get a fraction or a whole number out of it. Same for 72 and 162. Take the square root of those numbers are irrational. So they do not give us perfect whole numbers or perfect fractions. However, they may contain perfect square factors. In other words, can you rewrite 75 as the product of 2 numbers where one of those numbers is in fact a perfect square? Same for 72 and 162. We'll start with 75, noting here that 75 ends in a 5. This means that we can divide 75 by 5. Now, does that help us here? 5 goes into 75 15 times. 15 times 5 is 75. That is not, neither 15 nor 5 are perfect square factors. What about 3? How many times does 3 go into 75? I know that 3 divides 75 because 7 plus 5 is 12, and 3 divides 12. Thus, 3 will divide 75. 3 goes into 7 twice with 1 left over. 3 goes into the leftover 1 and 5, the leftover 15, 5 times. So that's 25. Thus, 3 multiply 25, 25 cents times 3 is 75 cents. For part A, we can rewrite 75 using our product rule because 75 can be rewritten as the product of 25 times 3. This is a true statement. 25 times 3 is in fact 75. We'll go to the full view here. We see here now that because we have our product rule for radicals, the square root of 25 times 3, the square root of u times v, this tells us this is equivalent to the square root of 25 multiply the square root of 3. And now we evaluate our perfect square factor under its own radical. The square root of 25 is 5. Thus, for the square root of 75, this is irrational. However, we can simplify down this irrational radical expression because our radicand contains a perfect square factor. We simplify out the perfect square factor and evaluate, giving us our simplified radical expression of 5 square roots of 3. For the square root of 72, 72 is an even number. 72 divided by 2 is 36. 36 is in fact a perfect square factor, and it is the largest perfect square factor that will divide 72. Consider 4. 4 is a perfect square factor. So is 9. 9 will divide 72 8 times. 9 times 8 is in fact 72. 9 is a perfect square factor. However, we want to choose the largest perfect square factor. So 4 will divide into 72, it's a perfect square. 9 will divide into 72, it's a perfect square. However, 36 is also a perfect square and will divide 72 twice. We will choose 36 because it's the largest perfect square factor for 72. So using our product rule to rewrite 72 as 36 times 2, thus the square root of 72 is equal to the square root of 36 multiplied the square root of 2. You can see this here. 36 times 2 is 72. Thus, the square root of 72 is equal to the product of the square root of 36 and the square root of 2. Evaluate the perfect square factor under its own radical. The square root of 36 is 6. Thus, the square root of 72 is equivalent to 6 square roots of 2. And again, this 6 square roots, this is 6 multiplied the square root of 2. In other words, square root of 2 plus square root of 2 plus square root of 2. Do that 6 times. That's why instead of doing repeated addition, we just write it as multiplication. Remember, that's what it means. Multiplication is repeated addition. We are adding the square root of 2 6 times, thus we have 6 square roots of 2. Now again, we said here the square root of 162 is irrational because 162 is not a perfect square, and it's under the square root sign. However, does it contain a perfect square factor? In other words, those perfect squares, 4, 9, 16, 25, 36, 49, etc. Do any of those numbers divide in to 162? Let's think about that there. Well, what I notice here immediately is, think about when you want to note division, summing up the digits. This helps us determine whether or not a number is divisible, or in other words, contains a factor of 3 or 9. Note here that 1 plus 6 is 7, plus 2 is 9. Now, because the sum of our digits is 9, 3 will actually divide into 9. Thus, 3 will divide into 162. But what's even more important here, because these digits sum up to give us 9, 9 will actually divide into 9, right? 9 divides into itself once. Thus, 9 will divide into 162. Why is this important? 9 is, in fact, a perfect square factor. So how many times does 9 divide in the 162? Well, 9 goes into 16 once. With 7 left over, 9 goes into 72 8 times. So here we have 9 multiply 18, which is in fact 162. 9 is a perfect square factor. So having the square root of 9 under its own perfect square, rather than its own radical, the square root of 9 is 3. Thus we have here 3 square roots of 18. But we're not done though. That's the challenging part here, is that now that we have our new radicand of 18, we ask ourselves, is 18 further factorable by a perfect square factor? Well, 18, 1 times 18, 3 times 6, 2 times 9, right? 2 multiplied 9 gives us 18, where 9 is a perfect square factor. So what we're going to do here is we're going to use this product rule one further time. 18 is 9 times 2. Thus, the square root of 18 is equivalent to the square root of 9 multiply the square root of 2. This is, of course, due to our product rule of radicals. Now, what do we have here? We have to evaluate the square root of 9, which is 3. So what do we have here? 3 multiply the square root of 9 multiply the square root of 2 is actually 3 multiply 3 multiply the square root of 2, where we simplify 3 times 3, which is 9. So after simplifying, after using our product rule twice, we see here that we get 9 square roots of 2. Now, why did we have to use the product rule twice? Remember that when we try to use the product rule, we want to choose the largest perfect square factor that is a factor of our radicand. Well, we started off with 9 times 18, where 9 is a perfect square factor. It just so happens that because 18 contained another perfect square factor, initially we just didn't choose the largest such perfect square. What would it have been? Is there a perfect square factor that's larger than 9? Well, can 16 divide into 162? No, 16 times 10 is 160, so 16 does not divide 162 wholly. What about 25? No, 25 can only divide things that end in a 0 or a 5. What about 36? Okay, 36, 72. Well, double 72, you get 144. Toss 36 on that one again, you're at 180. So not 162. What about 49? It ain't 49. What turns out here, the way that you can determine is we had this square root of 9 here and this square root of 9 that we simplified out. 9 times 9 is 81. 81 is a perfect square because it's 9 squared. 81 will divide 162 twice. 81 multiply 2 is 162. Thus, the square root of 81 multiply the square root of 2, right? If we would have chosen the largest perfect square factor for 162 initially, then our product rule use only one time. If you choose the largest one first, you'll only have to use the product rule once. 81 times 2 is 162. Thus, for our product rule, evaluating the perfect square to get us 9, and just using the product rule once, choosing the largest perfect square factor initially, we get the same exact simplified value, of course, as we would expect. Through equivalency, these all represent the same value. Our simplified value here of 9 square roots of 2. In the following exercises 1, 3, 5, and 7, simplify the radical. We've seen this similarly here, square root of 18. Thinking about all of the integer factors of 18, starting with the smallest. Well, of course, 1 multiply 18, but that's not going to help us here in simplifying the radical. So we go with the next integer, 2. 2 goes into 18 9 times, so we have 2 times 9. One integer up, we have 3. Does 3 go into 18? 6 times, 3 times 6. Going 1 up, we go to 4. Does 4 go into 18? It does 4 times, however, with a remainder of 2, so 4.5. So that's not going to help us here. We go to 5. 5 only divides integers that end in a 0 and 5. So we go to 6. We already have that listed. So these are the integer factors for 18. Are any of these factors perfect squares? 9 is a perfect square because it is 3 squared. Thus, the square root of 2 times 9 is, of course, the square root of 18. Using our product rule for radical expressions, we can express this as the square root of 9 multiply the square root of 2, and thus the square root of 9 is 3. And so we see here that the square root of 18 simplifies down to 3 square roots of 2. We know we are fully simplified because our new radicand of 2 is a prime integer. In other words, it will not contain a perfect square factor because it is prime. Now, you can have numbers that are composite that do not contain perfect square factors. For example, 10 is a composite number. However, 10 does not contain a perfect square factor. So that's how you know if you're done. How do you know you're done simplifying a radical expression? Does your radicand contain a perfect square factor if you're working with the square root? If you're working with any nth root, does it contain a factor to the power of n? In other words, here to a power of 2. 9 is 3 to the power of 2. That's why we extracted it. We factored it out. However, 2 is prime. It contains no perfect square factor. So we're done. Number 3, we have here the square root of 45. 45 is not a perfect square. However, it lives between the numbers 36 and 49, which are perfect squares. Thus, the square root of 45 is somewhere between 6 and 7. Square root of 45, we can simplify down if it contains a perfect square factor. Let's list the factors of 45. Starting with 2, 2 will not divide 45 because 45 is an odd number. Let's move up to 3. 3 will divide 45 because 4 plus 5 is 9, and 3 will divide 9. 3 will divide 45. 3 goes into 4 once with a remainder of 1. 3 goes into the remainder of 15 5 times. Therefore, 3 times 15 is 45. Adding 1 to the integer, let's go to 4. Once again, 4 will not divide into 45 because 45 is odd. Remember there that when you have an odd number such as 45, it's going to contain factors that are odd as well. What about 5? Again, 45 ends in a 5, therefore 5 will divide 45. 5 will divide 45 9 times. Are there any other integers? 6 will not. What about 7? 7 will not. 8 will not. And then we get up to 9, and 9 is already listed. Of these factors for 45, are any perfect squares? Again, we see yes because 9 is in fact a perfect square. Thus, the square root of 5 times 9, that of course is equivalent to the square root of 45. And now using our product rule for radicals, we break apart the square root of 45 into the square root of 9, multiply the square root of 5. We evaluate the perfect square. Square root of 9 is 3. Thus, we have 3 square roots of 5. And of course, we know we're fully simplified because 5 is our new radicand and it does not contain a perfect square factor because 5 can only be written as 5 times 1, and we cannot further simplify that. 1, of course, is a perfect square factor, but 1 is a factor of every number. 1 times 96 is 96, doesn't help us out. Thinking of 96, number 5, the square root of 96. Can we simplify this radical expression? Once again, thinking about the factors of 96, starting with 2. 2 divides 96 how many times? Well, if we split 96 in half, we're at, the way you think about this, how do you divide that by 2? Well, 100 divided by 2 is 50. 96 is very close to 100, so when we divide 96 by 2, our quotient should be pretty close to 50. And in this case here, 96 divided by 2 is 48. Of course, neither of those are perfect squares. They're not going to help us, so we go forward. Adding 1, we get 3. Can 3 divide 96? Well, 3 can divide a 9 and a 6. 9 plus 6 is 15. 3 divides 15. So 3 will go into a 9 3 times. 3 goes into the 6 twice. Thus, we see here 3 times 32 is, in fact, 96. Neither of those are perfect squares, so we move on. Adding 1, we get 4. Can 4 divide 96? Well, 4 goes into the 9 twice with 1 left over. 4 goes into the leftover 16 4 times. Thus, 4 multiplied 24 is 96. Notice how you can get this relationship here. Notice that this 2 to 4, so we're doubling the 2 to get to 4. We're having the 48 to get to 24. Is that not interesting that this is going to give us 96, this is going to give us 96, because a factor of 2 multiplies the 4, but where did that factor of 2 come from? It came from the 48. So if we move a factor of 2 over here to get 4, then we have to take away a factor of 2. 48 divided by 2 is 24. There's that relationship of doubling factors and thus having other factors. If I double 4, I get 8. If I half 24, I get 12. And note here, look at this. 8 times 12 is in fact 96. Interesting. Let's try that again. What happens if I double 8? If I double 8, I get 16. What happens if I half 12? I get 6. 16 times 6 is 96. What happens if I double 16 again? I get 32. What happens if I half 6? I get 3. And I would have to stop there because if I double 32 to get 64, how do I have 3? It's 1.5. Interesting. Is that true? Is 64 times 1.5 96? It is. Because 64 times 1 is 64. The 0.5 says half of 64 is 32. Add the 64 and 32, you get 96. So that rule actually applies even when you get down to rational values such as 1.5. 64 times 1.5. What if we double it again? 128 times 0.75 is 96. So that doubling rule for factors and the halving rule, so interesting that it will work for us here. Note that 16 times 6 is 96. 16 is a perfect square. 4 squared is 16. 6 is just 2 times 3. 6 contains no perfect square factor. Thus, square root of 96 is equivalent to the square root of 16 multiplied the square root of 6, where we evaluate the first radical. So we have here, square root of 96 is equivalent to 4 square roots of 6. And what do we know about the square root of 96? 96 is in between 81 and 100. Why is that significant? The square root of 81 is 9. The square root of 100 is 10. Thus, the square root of 96 is somewhere between 9 and 10. Let's try that out on Desmos, actually. Math tools, scientific calculator. What happens here if I type in the square root of 96? Will it give me a number between 9 and 10? And yes, it will. And because 96 is closer to 100 than it is 81, the square root of 96 is going to be closer to 10 than it will 9. Also note that if we write in 4 square roots of 6, we get the same output. We get the same value for our radical expression. And why do we expect that? It's because as we saw here in our PowerPoint, the square root of 96 is in fact equivalent to 4 square roots of 6. Using our product rule for radicals, square root of 96 is irrational. In other words, you cannot write that as a fraction. There's no way, because these numbers are just randomly being shot out as we go along. These decimals here will go on infinitely. Therefore, it is irrational. Think about that. A number that continues to go on infinitely just seems so irrational of a thought. A rational thought or a rational number is a number that we can work with. It's terminating. An irrational number is non-terminating. It will continue forever. And there is no pattern that we can predict here. Those numbers just keep randomly jumping back and forth from digits 0 through 9. Thus, 4 square roots of 6 is an irrational number. However, it is equivalent to the square root of 96 according to our product rule for radicals. And lastly here, the square root of 153. Let's think about the factors of 153. Once again, 1 multiply 153, but that's not going to help us. 2 will not divide 153, nor will any other even integers, right? Our number's odd, so our factors are going to end up being odd in this case here. So what do we think here? Can 3 divide 153? 1 plus 5 is 6, plus 3 is 9. Okay, there we go. Let's start with that. 1 plus 5 is 6, plus 3 is 9, thus 9. And again, this only works for the numbers 3 and 9. You cannot add the digits and say, oh, well, the digits add to 8, thus 8 will divide. That's not the case. For the numbers 3 and 9, for those factors, we can use the sum of the digits to determine. And now for 6 is interesting as well, because for 6, as long as a number is divisible by both 2 and 3, it's divisible by 6. What do we mean? If a number is even and the sum of the digits can be divided by 3, then it's divisible by 6. However, here, add the digits to get 9. 9 will divide into 153. 9 goes into 15 once with 6 left over. So now we have a remainder of 63. 9 will divide 63 7 times. Thus, 9 multiplied 17 is 153. And we're going to stop right here. We don't need to even try to look any further. Well, because there's not going to be any much more interesting factors other than 3 multiply 51. And that's not going to help us because 3 and 51, neither of them are perfect square factors. Here, we have a perfect square factor. Let's start here. 9 is 3 squared. Thus, rewriting using our product rule. Square root of 9 is evaluated as 3. Thus, we have 3 square roots of 17. This is equivalent to the square root of 153. And we know that we're done here because what is up with our radicand of 17? It's a prime number. In other words, it does not contain a perfect square factor. We can only write 17 as the product of 1 and 17. That will not help us further simplify. In other words, we're simplified with our radical expression. 3 square roots of 17. We can even go to Desmos to confirm this. 3 square roots of 17, so 3 multiply the square root of 17. All right, 12.369, and those numbers are irrational. This is an irrational value. Let's go ahead and type in the square root of 153. And we see here we get the same exact value. And I also want to show you that, multiplication is repeated addition. So if we have 3 square roots of 17, that's equivalent to the square root of 17 plus the square root of 17 plus square root of 17. See there that all 3 of those values are equivalent, as we would expect there, because all we're using there for the first one is the product rule for radicals, which states that those are equivalent. They're equal. They're the exact same values as you see here. 3 square roots of 17 is equivalent to the square root of 153, which is equivalent to the square root of 17 plus the square root of 17 plus the square root of 17. That's just our rule of multiplication. That's our definition. Multiplication is defined to be repeated addition. We have 3 square roots of 17. Thus, we have the 3 combined for addition. Exercise 11 and 12, simplify the radical when our radical is a decimal. Here for number 11, we have 4 hundredths. Now again, we can read this as 0.04 as our radicand, or the radicand of 4 hundredths. Now we're taking the square root of 4 of something. If we consider this here, is there anything that we can square to get 4 hundredths? In other words, if I imagine, what do I square to get 4? It's 2. 2 squared gives me 4. Now can I square 2 to get 4 hundredths? Now that necessarily wouldn't be the case. What about 2 hundredths? Maybe it makes sense that 2 hundredths multiplied 2 hundredths is 4 hundredths. Well, let's try that out. Well, think about this here. 2 hundredths I can actually express as the fraction 2 over 100, and thus multiplying 2 hundredths times 2 hundredths. Let's see what happens here. In the numerators, we multiply 2 times 2 to give us 4. However, in the denominators, 100 multiply 100 is 10,000. So this here is actually 4/10,000ths and not 400ths. If we expressed 4 over 10,000 as a decimal, let's try this out. 4 over 10,000, because the numerator is smaller than the denominator, we know this is some number between 0 and 1. Thus, 0 point what? Well, the 10,000 and the 4 tells us the first place here is the tenths place, then the hundredths, then the thousandths, then the 10,000ths. So how many 10,000ths do we have? We have 4 10,000ths, which is expressed as the decimal 0.0004. This would be 4 tenths, 4 hundredths, 4 thousandths, 4 10,000ths. So we want something that looks like this. We want 4 hundredths. So we see here 2 hundredths squared is 4 10,000ths. We need something smaller than 2 hundredths. Let's try 2 tenths. 2 tenths is 2 over 10. 2 tenths multiplied 2 tenths. 2 times 2 is 4. As we see here, 10 times 10 is 100. So what number, when you multiply to itself, gives you 4 out of 100? Again, this is expressed as the decimal 0.04. Again, that's the 4 tenths place. This is 4 hundredths. In other words, like 4 pennies, 4 cents out of a dollar. Here, 2 tenths multiply 2 tenths, or in other words, 2 tenths squared. Expressed as a decimal here, this is 0.2. We see here that 0.2 squared is going to equal 0.04. Thus, the square root of 0.04, the square root of 4 hundredths, is going to equal 2 tenths. The square root of 4 hundredths is equal to 2 tenths. Now let's take a look at number 12. Now that we've seen 11, 12 should be a little bit simpler for us, because we know here 25 hundredths, although that is not an integer, it is some rational number. Because we know 0.25, we can write that as 25 over 100. Now what is 25 hundredths here? Expressed as a fraction, 25 over 100. And the square root of 25 hundredths, 0.25, can be expressed in fraction notation, the square root of 25 hundredths. And now, using our quotient rule for radicals, property 2 down below, the square root of a fraction is the same thing as the square root of the numerator divided by the square root of our denominator. Well, as we see here, our numerator is a perfect square. 25 and 100, they are each perfect squares. The square root of 25 is 5. Square root of 100 is 10. Thus, the square root of 25 hundredths, 0.25, is the fraction 5 tenths, which we see 5 out of 10. 5 is exactly half of 10, thus 5 tenths reduces down to the fraction 1/2. That's interesting. The square root of 0.25 is equal to the fraction 1/2. That is because we express 0.25 as a fraction, take the square root of the fraction, and use our product rule, evaluate, simplify, and we have our value. Now, because we started off with a radicand and decimal value, let's actually express our output here in rational value. 1/2 expressed as a decimal, again, numerator smaller than denominator, thus it's some number between 0 and 1. 1/2 is exactly 50%, or 0.5. In other words, 0.5 squared is going to give you 0.25. Thus, the square root of 0.25 is 0.5. In other words, the square root of 25 hundredths is 5 tenths, or in other words, 1/2. For exercises 17 and 18, we will use the quotient property for radicals to simplify our radical expression. For the square root of 13/25, noting we do have a rational number under our radical sign, thus we will use our quotient rule. For the square root of 13 divided by the square root of 25, what do we notice here? Our numerator presents us with our own simplification challenge, and so does the denominator. Here we have the square root of 13, where 13 is a prime number. Thus, we can only write 13 as 13 times 1. Therefore, 13 does not contain a perfect square factor for us to further simplify. We are done with the numerator. What about the denominator, however? 25 is in fact a perfect square. The square root of 25 is 5, thus we evaluate. So we have here that the square root of 13/25 is equal to the square root of 13 divided by 5. Now, how can we rewrite this in terms of a radical expression? This is a fraction we have here. Well, the square root of 13 divided by 5, recall that to divide by 5 is to multiply by the reciprocal, which is 1/5. If you divide something by 5, it's the same as multiplying it by 1/5. Therefore, how many square roots of 13 do we have? If we divide a square root of 13 by 5, we have 1/5 of a square root of 13. In other words, 1/5 multiply the square root of 13. Now for number 18 here, we have the square root of 15/36. Well, looking at our numerator of 15 there, our radicand of 15, 15 is the product of 1 and 15, or 3 and 5. None of those factors are perfect square factors. We, of course, know 1 squared is 1, but 1 will not help us simplify our radicand. Thus, 15 does not contain a perfect square factor, of course, other than 1. However, for our denominator, the square root of 36 is in fact 6. Thus, we write this as the square root of 15 divided by 6. And for the same dilemma we see above here, if you have a radical expression, the square root of 15 divided by 6, we see that our radical is in the numerator. Now, that's okay. Later on, we will see that if our radical is in the denominator, we will use rationalization techniques to get rid of the radical in our denominator here. A radical divided by 6, thus, we have here 1/6 multiply the square root of 15. This just shows us in terms of the radical, how many of the radical do we have? For the square root of 15, we have 1/6 of the square root of 15. We don't have 1 square root of 15. We don't have 2 or 3 square roots of 15. We have less than 1. We have 1/6 square root of 15. For simplifying radical expressions to any nth root, not just the square root, we have here that a radical expression is said to be in simplest form if all 3 of the statements below are true. First one here, all possible nth powered factors have been removed from each radical. 2, no radical contains a fraction. 3, no denominator of a fraction contains a radical. For part A, we're looking at the cube root of 40. Here we note that 40 is not a perfect cube, and we can go through the list. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. Thus, the cubic root of 40 is going to be some number between 3 and 4. That's because 3 cubed is 27 and 4 cubed is 64. 40 is somewhere between 27 and 64. Thus, the cubic root of 40 will be some number between 3 and 4. How can we simplify out this irrational value, this cubic root of 40? We simplify by determining, are there any factors of 40, any perfect cube factors? In other words, some factor such that we could rewrite that factor to the third power. Let's think about the factors of 40, 2 and 20, 4 and 10, 5 and 8. Are any of those factors perfect cube factors? Well, I take you to the example with 8 times 5. 8 times 5 is 40, where 8 is a perfect cube. 8 is the result of 2 cubed. Thus, for part A, the cubic root of 40, using our product rule for radicals, and yes, our product rule for radicals will work for any n-powered radical, not just the square root. Here we have the cube root. Well, 40 is 8 times 5. Thus, the cube root of 8 multiplied to the cube root of 5 will give us the cube root of 40. We write it as such because now the cube root of 8 can be simplified down to 2. Thus, the cubic root of 40, or the cube root of 40, is equal to 2 times the cube root of 5, or 2 cube roots of 5. Part B here, we have the fourth root of x to the fifth power. Now note here we are starting to work with the example of our radicand involving variables or variable expressions. Here our radicand is x to the fifth power. Notice there again we have 5 factors of x, x to the fifth power. We're working with the fourth root of x, or excuse me, we're working under the radical sign that is the fourth root. In order to simplify radical expressions, are there any fourth powered factors within x to the fifth power? In other words, can we rewrite x to the fifth power as the product of 2 or more expressions where one of those expressions is some variable to the fourth power? Well, of course, using our product rule for integer exponents in section 1 of chapter 5, x to the fifth power can be expressed as x to the fourth power multiply x to the first power. Of course, we're just adding exponents to combine like bases when they multiply. Thus, we can break apart x to the fifth as the product of x and x to the fourth, also the product of x squared and x cubed. Each of these products will give us x to the fifth. And of course, we are choosing the product of x to the fourth and x for x to the fifth because as you see here, x to the fourth power underneath the fourth root, this is the example of our inverse property that we saw in section 1 of chapter 9. The fourth root of x to the fourth power, the exponent of 4 and the root here, the index of 4, they will cancel with one another. It's just like adding and subtracting the same number will cancel. Multiplying and dividing by the same number will cancel out the properties. Here, taking a number and raising it to a power and then taking the nth root, that same exact power there, they will cancel. Thus, the fourth root of x to the fourth is simply the x. Thus, we see here the fourth root of x to the fifth power. Is there a perfect fourth power in this radicand? Yes, it's x to the fourth power. X to the fourth power multiplying x gives us x to the fifth. Thus, the fourth root of x to the fifth, when extracting out that perfect fourth power of x, x to the fourth, when we pull it out of the radical, it is just x. Thus, we have x multiply the fourth root of x. With part A, we have the square root of our fraction 81/25. We see there, step 2 says no radical contains a fraction. If we want to simplify this expression, we need to break apart that fraction. Quotient rule for radicals says we can take the square root of the numerator and divide it by the square root of our denominator. Easily enough here, the square root of 81, 81 is a perfect square. It is 9 squared. Thus, the square root of 81 is 9. The square root of 25 is 5. So as we see here, because our result here is 9/5, 9/5 is a fraction. That's a rational number. It's not irrational. What does that mean for 81/25? This is a fraction that is a perfect square fraction. In other words, if you take this fraction 9/5 and you square 9/5, you're going to get 81/25. Square the 9 to get 81, square the 5 to get 25. Thus, when you take the square root of those numerator and denominator, you will get 9/5. What about part B here? Part B already has the numerator and denominator under its own radical. Thus, for the numerator, we will simplify the square root of 56x squared. Note here that 56x squared, right? We have a factor of 56 and a factor of x squared. Well, according to our product rule in our numerator, the 56 we will place under its own radical. The x squared we will place under its own radical. What do we think we want to do here for part B? In the numerator, the square root of 56 is multiplying the square root of x squared. Starting with the factor square root of 56, does 56 contain any perfect square factors? We have 2 times 28, 4 times 14, and 7 times 8. Well, let's stop at 4 times 14. 4 is a perfect square factor. Thus, 4 times 14 to give us 56, we will use that for our product rule. Staying in the numerator, what about the square root of x squared? Again, think about it. We have x squared and we're taking the square root. The square root radical and the exponent will cancel, leaving us with x. And in our denominator, 8 is not a perfect square factor. 4 and 9 are perfect square factors. 8 is in between 4 and 9. Thus, the square root of 8 is in between 2 and 3. Does 8 contain a perfect square factor? Just as we saw for the square root of 56, 8 is 4 times 2. Thus, we can write the square root of 8 as the square root of 4 times the square root of 2. 4 times 14 for 56, thus product rule. 4 times 2 is 8, thus our product rule. What do we see we can do here? We can cancel. Canceling the common factor for square root of 4, which is, of course, 2. We had a factor of 2 there in the numerator and denominator, thus we cancel, and we have a more simplified expression. But what do we have left? The square root of 14 times x divided by the square root of 2. One moment. And we're back. So we have three factors here. We have a factor of square root of 14, a factor of x, and a factor of square root of 2, except square root of 2 is in our denominator. Let's actually think about this in terms of our real numbers, square root of 4, square root of 14. This, of course, is multiplying the x in the numerator, but this is all being divided by the square root of 2. What I'm going to do is I'm going to carefully and purposefully choose the square root of 2. I'm going to divide it not by the entire numerator, but I'm going to move it over here with the real number, because this will allow me to further simplify using our quotient rule. The square root of our numerator divided by the square root of our denominator, rewriting this using the quotient rule, working in the reverse direction, the square root of 14 divided by the square root of 2 is equivalent to the square root of our fraction 14 halves. And as you see here, under our radical, the fraction 14 divided by 2 will simplify down to 7. Thus we have here, for part B, the square root of 56x squared divided by the square root of 8, simplified down is the square root of 7 multiply our variable x. Simplify the radical expression for the following exercises 19 through 27. For 19, we have the square root of 9x to the 5th power. Our radicand, 9 multiply x to the 5th power. Thus, by using our product rule for radicals, we will separate the coefficient 9 and the variable expression x to the 5th. Because they are multiplying under the radical, we will use the product rule to break apart each of these factors under its own radical and then simplify. So as we see there for number 19, this is equivalent to the square root of 9 multiply the square root of x to the 5th power. So what do we see going on here? We evaluate the square root of 9 and we get 3. But now we have to deal with the square root of x to the 5th power. And we're thinking here, is x to the 5th power a perfect square? Well, neatly here, if we're dealing with the square root, what are perfect squares when dealing with the variable? Well, we said previously the square root of x squared is simply x, because our inverse property states that the exponent of 2 and the root of 2 for the radical will cancel. Square root squared cancel, leaving us with x. What about x to the power of 5? So here we have 5 factors of x under the radical. Well, neatly enough, once again, using our product rule for integer exponents, we can rewrite x to the 5th power as x squared multiply x. Of course, that gives us the 5 factors of x. Note again here that x squared multiply x. This implies 5 factors of x, thus x to the power of 5. Using the product rule for radicals here, breaking apart the factors of x squared, and x under their own radical, we now can evaluate because the square root of x squared using the inverse property is simply x. So we get 2 factors of x here, and thus our square root of x, this x under the radicand will stay because we cannot further simplify this radical here. 3 times x times the square root of x, which we will simplify, as 3x squared times the square root of x. Now, one interesting thing here is that there's sort of a shortcut, a rule of thumb for dealing with our variable expression. This is a variable with some exponent underneath a radical, whether that radical is the square root, cube root, or in general any nth root. Note here that our base, our index for the radical is understood to be 2. The initial problem we had there, 9x to the 5th power under the radical, therefore the square root of 9 multiply the square root of x to the 5th power. Here's something we can consider. Well, we know square root of 9 is 3, that part's done. But how do we deal with the square root of x to the 5th power? The way that I like to think about this is, how many times will the root of 2 divide into the exponent of 5? How many times will 2 go into 5? Well, twice, right? 5 divided by 2 is 2 with the remainder of 1. What does that mean with our exponents here? Well, because we have a power of 5 for our variable x under a root of 2, 5 divided by 2 is 2 with the remainder of 1. What this means here, we are going to factor out 2 factors of x, in other words, x squared. Again, 5 divided by 2 is 2 with the remainder of 1. What does the remainder of 1 mean? It means we are going to leave behind 1 factor of x under the radical. And there it is there. So again, the shorthand notation there is just considered division. Because what does that mean here again? Rewriting this as a rational exponent, the square root of x to the fifth power is x to the 5/2 power. And how do we get x to the 5/2 power? Well, it's x to the 2/2, x to the 2/2, which is 4/2, and then you have an extra half there. So x to the 2/2 is simply x to the first, which is x. X to the 2/2 is x, and then x to the 1/2 is understood to be the square root of x. So many ways we can think about breaking down this simplification here, but the easiest one is to understand the inverse property. How can I use from chapter 5, section 1, the product rule for exponents to rewrite x to the fifth? X squared times x. Why is that significant? The square root of x squared is simply x. Square root of x squared is x. Square root of x cannot be further simplified. It stays. Of course, evaluate square root of 9 to be 3, giving us our fully simplified expression of 3 multiply x squared multiply the square root of x. For number 21, the square root of 48y to the fourth power. Again, 48 is multiplying y to the fourth, so we'll use our product rule to break apart the coefficient and the variable. Here we have a radicand of 48 under the radical. Unlike number 19, 9 under the radical, 9 is a perfect square. However, 48 is not a perfect square. 49 is, 48 is not. Thus, the square root of 48 is going to be some irrational value a little bit less than 7. So how can we simplify this radical expression? Using our product rule for 48, how can we rewrite 48 as the product of two numbers such that one of those numbers is a perfect square? Well, 4 times 12 will do exactly that for us. Now the question here is there any larger perfect square factor for 48? And I believe we have seen this example before. 4 times 12 is one example. However, 16 times 3 will give us 48, where 16 is a perfect square, and that's the largest such perfect square that 48 contains. So we'll rewrite 48 as the square root of 16 multiply the square root of 3. However, for the square root of y to the fourth power, of course, this is going to now multiply the square root of y to the fourth power. And using that shorthand notation there, our index or our root is understood to be 2 because it's a square root. Our exponent for y is 4. 4 divided by 2 is 2 with the remainder of 0. Exponent 4, root of 2. 4 divided by 2 is 2 with a remainder of 0. What does this mean? We are going to factor out 2 factors of y from our radical. A remainder of 0 means we will leave behind 0 factors of y under the radical. In other words, there will be no square root of y or anything like that because y to the fourth power just so happens to be a perfect square. How is y to the fourth power a perfect square? It's the result of squaring y squared. What happens here if you square y squared? Well, our power to a power rule says multiply exponents. 2 times 2 is 4. Thus, because y squared squared is y to the fourth, the square root of y to the fourth is y squared. Another way to see that, as we said here, y to the fourth power is y squared multiply y squared. Thus, if we were to rewrite y to the fourth power as y squared times y squared, and thus use our product rule to break apart each factor under its own radical, just as we've seen for the variable x, the square root of x squared is x, thus the square root of y squared is y. If we have 2 factors of y, we have y squared. So think of it like that. Because our root is understood to be a 2, our exponent is 4. Because our exponent divided by the root was a value that had no remainder, that means that y to the fourth is in fact a perfect square. Square root of 16 we evaluate to give us 4. Thus we have here 4 multiply the square root of 3 multiply y squared. And to have it in a proper form, what we're going to do here is actually going to take the y squared and switch it, commute it with the square root of 3. And we do this to ensure to the reader this y squared is not under the radical. We may accidentally extend this radical notation further than we want, and it may perceive as the y squared is a part of this radicand with the 3, but we don't want that to be the case, right? Y squared is its own factor outside of our radical expression. So here, 4 multiply y squared multiply the square root of 3. Exercise 23, the square root of 117 multiply y to the power of 6. For the product rule, we have the square root of 117 multiply the square root of y to the 6th power. For 117, we notice this is an odd number, literally, because it ends in a 7. So it is not divisible by 2. The question is it maybe divisible by 3? Well, again, we want to know, is it divisible by any number that is a perfect square? Those numbers such as 4, 9, 16, 25, 36, etc. Let's start with 4. Because this number is odd, 4 will not divide into 117. Thus, 4 is not a factor of 117. Let's go to the next perfect square, which is 9. Note here that 117, if you sum the digits, 1 plus 1 plus 7, you get 9. And that's the interesting thing about 9. How do you know if a number can be divided by 9? In other words, how do you know if a number has a factor of 9? Simply add together the digits. If 9 will divide into the sum of the digits, 9 will divide into the number. In this case here, 9 will divide into 117. Thus, 9 is a factor of 117. How many times will 9 divide 117? Well, let's think about this here. 9 cannot divide into the first digit 1. And the way that you break this up, right, what is the number 117? Well, it's 100 and 10 and 7. So we want to know, how does 9 divide into 117? Well, we know, how does 9 divide into the 100? How does it divide into the 110? How does it divide into the 117? That's where our long division algorithm comes into play. 9 does not nicely divide into 1, which is the 100, but 9 will go into the 110. Think about this. 9 multiplied 12 is 108. So we know that it's at least 12, right? And it turns out that if you add another 9 to 108, you get 117. Thus, 9 times 13 is 117. Another way to do this, 9 goes into the 11 one time with 2 left over. Thus, the 2 left over in the 7 is 27. 9 goes into 27 3 times. Thus, we see here 9 times 13, or in other words, if you add 9 13 times, you'll get 117. Also, if you add 13 9 times, you'll get 117. What's the takeaway here? 9 is a perfect square factor of 117, thus the square root of 9 is 3. Can we further simplify the square root of 13? Well, does 13 contain a perfect square factor? 4, 9, 16, well, 16 is too large. Is 4 and 9 a factor? No, because 13 is a prime number, thus the only integer factors for 13 are 13 and 1. So that will remain the same because we cannot further simplify. However, the square root of y to the 6th power, notice again here that we are taking the square root, so our root is understood to be 2. Our exponent is 6. Because our exponent is an even number underneath the square root, y to the 6th power is in fact a perfect square. What do you have to square in order to get y to the 6th? It's y cubed. And we know this here because exponent 6 divided by the root of 2, 6 divided by 2 is 3 with a remainder of 0. What does this mean? It means we will factor out 3 factors of y. The remainder of 0 tells us we will leave behind 0 factors of y underneath our radical. Thus, 3 multiply the square root of 13 multiply y cubed, which in the proper form thus we have here 3y cubed times the square root of 13, or 3 times y cubed times the square root of 13. How do we do this for 25 and 27? Same concept, right? For 25, our radicand is 120 multiply x squared multiply y cubed. So for each of those factors, using the product rule, we will take each of those factors and place them under their own radical sign. For number 27, 192 is multiplying a to the 5th power, which is multiplying b to the 7th power. Once again, the product rule states take the 192, place it under its own radical, take a to the 5th power, place it under its own radical, take b to the 7th power, and place it under its own radical, and then look to simplify each of the individual radical expressions. So for 25 here, 120, x squared, and y cubed. So taking them, placing them under their own radical. We look at 120 first. 120 is not a perfect square. 121 is, right? The square root of 121 is 11. Thus, the square root of 120 is going to be an irrational value, a little bit smaller than 11. However, does 120 contain a perfect square factor? It is even. So looking at 4, does 4 divide 120? It actually does. It divides it 30 times. 4 goes into 12 3 times. 4 goes into 0 0 times. Thus, 4 times 3 is 12. Therefore, 4 times 30 is 120. 4 is a perfect square factor. However, is there a larger one? Well, what about 9? If you add the digits, 1 plus 2 plus 0 is 3. 9 does not divide 3, thus 9 will not divide 120. What if we jump up to 16? Will 16 go into 120? Well, half of 16 is 8. Thus, 16 times 5 is 80. 16 times 6, if you add 16, that's 96. Then 112, then 128. So it actually will not divide 120. Jumping to the next one, 25. 25 will divide numbers ending in a 0 or a 5. 25, 50, 75, 100, 125. So it won't divide 120. 49 won't. 64. So it seems like it might be 4. Let's write 4 times 30 using our product rule. The square root of 4 multiply the square root of 30 will give us the square root of 120. For the square root of x squared, using our inverse rule, the square root of x squared, our exponent of 2, and the radical that is the square root will cancel, leaving us with x. And that is a factor of x, and if it helps you understand, let's put it in parentheses. It lets the reader know that we are multiplying by that factor of x. Now, what about the square root of y to the third power? Notice that if we're comparing the y and the x has 2 factors, y has 3 factors. So there's more over here. There's more going on over here. But what do we know about y cubed? Y cubed is the product of y squared and y. Thus, understanding that our root is 2, 3 divided by 2 is 1 with a remainder of 1, right? How many times will 2 go into 3? 2 goes wholly or fully into 3 once with a remainder of 1. This means that for the 1, we are factoring out 1 factor of y. What does the remainder of 1 mean again here? 3 divided by that understood, unwritten root of 2. 3 divided by 2 is 1 with a remainder of 1. The remainder of 1 tells us how many factors of y to leave under our radical sign. The remainder of 1 says leave 1 factor of y under the radical. Going back to the front, square root of 4 is in fact 2. Taking all of our factors and pulling them out front here, we have a factor of x and y. Now, what can we do with our square root of 30 and our square root of y? Notice here that this 120 left us with a 30 under the radical. This y cubed left us with a y under the radical. Thus, the square root of 30 multiplied the square root of y. Because we cannot simplify those two radicals, we will just bring them back together for our full simplification. Remember, our radical expression is only going to contain one radical sign. Thus here, once we simplify the square root of 4 to 2, 2xy times the square root of 30 times the square root of y, we will simply say 2xy times the square root of 30y. We know we are fully simplified with our radical expression if we cannot further simplify our radicand. The 30 here, 30 is 2 times 15, 3 times 10, 5 times 6. None of those factors are perfect square factors, thus we cannot further simplify the square root of 30. Y is one factor of y. Y is a prime factor by itself, thus we cannot further simplify the square root of y, giving us our simplified radical expression. Number 27, the square root of 192 multiply a to the power of 5 multiply b to the power of 7. Using our product rule to break apart the factors under their own radical, square root of 192 multiply the square root of a to the 5th power multiply the square root of b to the 7th power. Here, for the square root of 192, 192 is not a perfect square. However, it is between our perfect squares of 13 squared and 14 squared. 13 squared is 169, 14 squared is 196. Thus, the square root of 192 will be irrational, and it'll be just below 14. Does 192 contain a perfect square factor? Starting with the smallest factors that are perfect squares, 4, 9, 16, 25, and so on, we see that 4 is a factor of 192. However, 16 is also a factor of 192. And how many times will 16 divide 192? 16 goes into 19 one time, with 3 left over, giving us a remainder of 32. 16 divides 32 twice. So we see here that 16 times 12 is in fact 192. But as soon as I do this, I see 16 is a perfect square, but 12 here, notice here that 12 can be rewritten as 3 times 4. Okay, so notice here that this remaining 12 factor actually contains a factor that is a perfect square. So what is the largest such perfect square factor that will divide into 192? Watch this. If I take this perfect square factor of 16 and this perfect square factor of 4 and multiply them together, 16 times 4 is 64. So what actually is the largest such perfect square factor for 192? Well, 16 times 3 times 4 is going to give me 192. If I do some rearranging here, 16 times 4 is 64. Thus, 64 times 3 is also going to give me 192. These are two other factors for 192, where 64 is a perfect square factor, and it's much larger than the 4 or 16. So the factorization we want to use here to rewrite our product rule for 192, we want to rewrite it as the square root of 64 multiplied the square root of 3. Using our product rule for radicals, this is the largest such perfect square factor for 192. Thus, we will evaluate by simplifying square root of 64 multiply the square root of 3. For the square root of a to the 5th power, where our root is understood to be 2, right? If it's not written, it's understood to be the square root. Exponent of 5, 5 divided by 2 is 2 with the remainder of 1. What does that mean again? 2 with the remainder of 1. We will factor out 2 factors of a. The remainder of 1 says leave behind 1 factor of a. So a to the 5th power under the square root, it says how many perfect squares live underneath our radical for a to the 5th power? 2 factors of a. There are 2 factors that are perfect squares because a to the 5th power is a squared times a squared times a. 2 plus 2 plus 1 is the 5 factors of a. Thus, if square root of a to the 5th gives us, according to our product rule, square root of a squared times square root of a squared times square root of a, using our inverse rule here, canceling, we get a factor of a here. Inverse property to cancel, we get a factor of a here. Thus, 2 factors of a get factored out of the radical, giving us the a squared, multiply the square root of a. Same concept with b to the 7th power. 7 divided by 2. How many times will 2 go into 7? 2, 4, 6, 8. Oh, we got to hold up. 2, 4, 6 with the remainder of 1. 7 divided by 2 is 3 with the remainder of 1, indicating for us 3 factors of b will be factored out under the radical. The remainder of 1 indicates we will leave behind 1 factor of b. Notice what's happened here so far. When we are dealing with variable expressions under the radical, what have we seen? For exponents such as for number 19, x to the 5th power, that's an odd exponent 5. We left behind 1 factor of x for number 19. For number 21, y to the 4th power, 4 is an even exponent. And notice for number 21, we left behind 0 factors under the radical. Everything was factored out. Y to the 4th power is a perfect square because its exponent is even. Likewise for 23, y to the 6th power is a perfect square because its exponent is even. Y to the 4th power is y squared squared. Y to the 6th power is y cubed squared. X to the 5th, because 5 is odd, that is not a perfect square. Thus, we left behind 1 factor of x. For number 25, x squared, exponent is even, and we know that x squared is a perfect square because it's the result of squaring x. Y to the 3rd power, that's not an even exponent. Y cubed is y squared times y. It contains a perfect square factor, but it itself is not a perfect square because its exponent is odd. Likewise, for a to the 5th and b to the 7th, they contain perfect square factors, a squared and a squared, b squared, and b squared. Which, what does that also mean? A to the 5th power, we said was a squared, and a, but isn't also a to the 5th power a to the 4th times a? A to the 4th power is a perfect square. As we saw, if y to the 4th, if we take the square root of y to the 4th and we get y squared, then surely the square root of a to the 4th is a squared. Just basically interchange the variable and the rule applies the same. That property works. That is our inverse property that's allowing us to do so. So under the square root sign, if our exponent is even, we have a perfect square factor, and there will be no factor remaining under the radical. If our exponent is odd, however, underneath our square root sign, we will leave behind 1 factor of that variable. So for number 27, further simplifying here, the square root of 64 is 8. The a squared and the b cubed, we will move out front. What remained under our radical? We have 3 factors, the square root of 3, the square root of a, and the square root of b. Well, according to our product rule, if we can break apart our radical into 2 or more factors under the radical, well, we can take our factors under the radical and bring them together under 1 radical expression. multiplication here. So the 3 multiply a multiply b. And that's why we're allowed to do so, right? Is because although these are not sitting next to one another, the commutative property of multiplication says we can move around these factors wherever. We switch those two factors, we switch those two factors, and we then switch the middle factors to just take the a squared and b cubed and move them in the front, take the radicals and move them to the end, and then bring them together into one radical. We can do this here because each of these radicals are factors for our radical expression, thus giving us our simplified radical expression for 27, 8 multiply a squared multiply b cubed multiply the square root of 3ab, where our new radicand for our radical expression is 3 times a times b. As we've discussed, our product and quotient rule for radical expressions will extend to roots larger than or equal to 2. We have seen many examples where our root is equal to 2, thus working with the square root radical. Here for number 40, we have the fourth root of 128 multiply u to the fourth power multiply v to the seventh power. Note here that we will now look for factors that are perfect nth factors, in other words, perfect fourth factors. In other words, for 128, is it a perfect power of 4? Is there some number such that when you raise it to the fourth power, you will get 128? Well, if we think about this here, let's think about 3 to the fourth power. Let's think 2 to the fourth power. 2 to the fourth is 2 times 2 times 2 times 2, which is 16. 16 will divide into 128 8 times. But what about 3 to the fourth power? Can 3 to the fourth power divide into 128? 3 to the fourth is 3 times 3 times 3 times 3, which is 81. Can 81 divide into 128? No. What about 4 to the fourth power? 4 times 4 times 4 times 4? Well, 4 cubed is 64. And if we multiply that by 4, we get 256, which is larger than 128. It's actually double 128. So because 128 is somewhere between 256 and 81, it means that the fourth root of 128 is going to be somewhere between 3 and 4, some number between 3 and 4. So 128 is not a perfect fourth power. However, does it contain a factor that is a perfect fourth power? Well, those small fourth powers that we looked at, 2 to the fourth and 3 to the fourth, that was 16 and 81 respectively. 81 does not divide 128. However, 16 does. It divides 128 8 times. 16 times 8 is 128. Thus, we will write the fourth root of 128 under its own radical. And by using our product rule, because 16 times 8 is 128, we will use our product rule to write it as the fourth root of 16 multiply the fourth root of 8. We are doing this because the factor of 16 is a perfect fourth power. It's 2 to the fourth power. So we will easily evaluate the fourth root of 16. By looking at our variable u to the fourth under its own radical, the fourth root of u to the fourth power, note here that our exponent 4 for our variable u and the root of 4, the fourth root, power of 4, those are inverse properties. They cancel with one another. The fourth root of u to the fourth, just like the square root of u squared is u, the cubic root of u to the third power is u, the fourth root of u to the fourth power is u. Exponent cancels with the root of 4. Likewise, exponent divided by the root, what happens? 4 divided by 4 is 1 with the remainder of 0. This means to factor out one factor of u. The remainder of 0 means to leave behind 0 factors of u. Thus, inverse property, fourth root of u to the fourth is the factor of u. Here, the fourth root of v to the seventh power. Does v to the seventh power contain a perfect fourth power? Well, v to the seventh is 7 factors of v. That means we have 4 plus 3 factors of v. Thus, v to the seventh is the fourth root of v to the fourth multiply v cubed. And the fourth root of v to the fourth is just v, leaving behind 3 factors of v under our radical. In other words, 7 divided by 4 is 1 with a remainder of 3, implying we factor out one factor of v. The remainder of 3 tells us to leave behind 3 factors of v under our radical, the fourth root of v cubed. So notice here, we had 7 factors, we leave behind 3, because 4 factors of v under the fourth root will factor out to our factor of v outside of the radical. Thus here, the fourth root of 16 we evaluate to give us 2. Our factor of u and factor of v will move out front, leaving us now with 2 factors under our radical. We have the fourth root of 8 multiply the fourth root of v cubed. We cannot further simplify either of those radicals. Thus, we combined the radicands. with multiplication. 8 multiply v cubed will become our radicand under our single radical expression. Thus, for number 40, our simplified radical expression is 2 times u times v times the fourth root of 8v cubed, where 8v cubed is our new radicand for our radical. For number 42, we have the cube root of 16x to the fourth y to the fifth. Our radicand, 16 multiply x to the fourth multiply y to the fifth. Thus, our product rule for radicals here, we will take each factor, 16x to the fourth y to the fifth, and place them under their own radical. Here, our root is 3. This is the cube root. Therefore, the root is equal to 3. The cube root of 16 is 16 a perfect cube. We think about our perfect cube values. 2 cubed is 8. 3 cubed is 27. 16 is in between 8 and 27. Thus, the cube root of 16 is irrational. And the cube root of 16 will be some value between 2 and 3. So 16 is not a perfect cube. However, does it contain a factor that is a perfect cube? We just said 2 cubed was 8. 8 will divide 16 twice. Thus, using our product rule for the cube root of 16, we get that the cube root of 16 is equivalent to the cube root of 8 multiply the cube root of 2. We will evaluate here and simplify, but first let's go ahead and move on to the variables. We have x to the fourth power underneath our cube root. Recall previously we said that x to the fourth is a perfect square. The question here now, is it a perfect cube? It's under the cube root, so we have to switch our thinking here. Well, the cube root here asks us, do we have a perfect third power? Well, x to the fourth power is not a third power, it's a fourth power. However, x to the fourth power consists of 4 factors of x, which we can rewrite as x cubed multiply x. Thus, for x to the fourth power under the cube root, we express it as the cube root of x cubed multiply the cube root of x, because as we see here, x cubed times x does give us x to the fourth. Same thing with y to the fifth, that is a fifth power. We're looking for a perfect third power. Well, here, 5 and 3, 5 divided by 3 is 1 with a remainder of 2. What does that mean here? It means that if we rewrite y to the fifth power as y to the third multiply y to the second and place them under their own radical, we will now see that the cube root of 8 is 2. The cube root of x cubed, the exponent and the root cancel, leaving us simply with x. The cube root of y cubed, similar to the variable x, cube root of y cubed is y. So we are left with 3 factors under radicals that cannot be further simplified. The cube root of 2, the cube root of x, and the cube root of y squared cannot be further simplified. Thus, because they are factors, our product rule says that we can combine them into one radical by multiplying the radicands together. 2 times x times y squared. So what do we have here for our simplified expression for 42? For number 42, the cube root of 16x to the fourth y to the fifth will simplify down and is equivalent to our simplified radical expression, 2 times x times y times the cube root of 2xy squared. For exercises 47, 49, 51, and 53, simplify the radical expression where our radicand is a fraction. Starting with 47, the square root of our fraction 32 a to the fourth over b squared. We see here that by using our quotient rule for radicals for 47, we will write the square root of our numerator divided by the square root of our denominator. So we have here the square root of 32a to the fourth. And this will be divided by the square root of b squared. So we see we just have a little numerator problem we'll have to simplify and a denominator problem we'll have to simplify. In our numerator, our radicand 32 times a to the fourth power. Go to the full view here. There we go. We see here the square root of 32a to the fourth power. 32 is multiplying a to the fourth. So for our product rule there, the square root of 32 multiply the square root of a to the fourth. 32 is not a perfect square. It is between 25 and 36. Thus, the square root of 32 is between 5 and 6. Does 32 contain a perfect square factor? What is the largest such perfect square factor? Well, 4 times 8, 16 times 2, where 4 is a perfect square factor, and so is 16. 16 is larger, so we'll choose that. The square root of 8 to the 4th power, because we have 8 to the 4th under the square root, our exponent is even. 8 to the 4th power is a perfect square. What do you have to square to get 8 to the 4th? You square a squared to get 8 to the 4th. Thus, the square root of 8 to the 4th is a squared. And thus a squared is a factor. In the denominator, b squared is our radicand under the square root. B squared, because the exponent is even, b squared is a perfect square. Of course, it is the result of squaring b. Thus, the square root of b squared, according to our inverse property, is b. For our numerator, we evaluate the square root of 16 to give us 4. Taking the a squared and switching it, commuting it with the square root of 2. For radical expressions, we typically move the radical to the right. And actually here, if we would like to, we could now make this a more proper radical expression by writing the coefficient fraction out front, multiply the square root of 2. So either would be acceptable here because, of course, square root of 2 multiply the fraction. This factor of square root of 2 just goes in the numerator, giving us our following radical expression. Going back to the PowerPoint there, looking at number 49, we have the fifth root of our fraction 32x squared over y to the 5th power. For the numerator, 32x squared divided by the 5th root of y to the 5th power. For our numerator here, we see we are dealing with 32 and x squared. Spreading them apart there, 32 and x squared separately under their own 5th root radical. Well, note here, 32 actually is a perfect 5th power. It's 2 to the 5th power. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Thus, the 5th root of 32 is 2. What is the 5th root of x squared? X squared contains 2 factors of x. 2 factors of x under the 5th root cannot simplify out. Thus, we will leave the x squared under the 5th root radical. This is divided by the 5th root of y to the 5th power. We see here the exponent of 5 and the root of 5 are exactly the same. Thus, they cancel due to our rule of the inverse property. The 5th root of y to the 5th power is simply y. 2 times the 5th root of x squared divided by y, or if we write it in terms of a radical expression, we have the fraction 2 over y multiply the 5th root of x squared. Exercise 51, the cube root of the fraction 54 a to the 4th divided by b to the 9th power. Using our quotient rule of radicals, we will take the cube root of our numerator divided by the cube root of our denominator. For our numerator, the cube root of 54 a to the 4th power, our product rule allows us to take the factor of 54 and place it under its own radical, as well as the factor a to the 4th power, giving us here our quotient, that is the cube root of 54, multiply the cube root of a to the 4th power divided by the cube root of b to the 9th power. Keep in mind here that our radical expression simplification steps tell us that all of the nth powered factors have been removed from each radical. In other words, here with our root of 3, any third powered factors, any base to the power of 3. Step 2, no radical contains a fraction. We no longer have a radical with a fraction due to our product rule. We broke it apart. And step 3, no denominator of a fraction contains a radical. Right now we have a radical in our denominator, so we need to find ways to get that taken care of. We'll go to the full view. 54 is not a perfect cube. 3 cubed is 27, 4 cubed is 64. Thus, the cube root of 54 is somewhere between 3 and 4. Does 54 contain a perfect cube factor? Well, we just said 3 cubed is 27, and 27 is half of 54. Thus, 27 times 2 gives us 54. The cube root of 27 multiply the cube root of 2 will give us the cube root of 54, so we did our correct rewriting there. For the cube root of a to the fourth power, again, consider, is a to the fourth a perfect cube? It is not. There are 4 factors of a, which means we have, living inside of those 4 factors of a, we have 3 factors. Another way to think about this, 4 divided by 3 is 1 with a remainder of 1. A to the fourth is a cubed times a. Thus, the cube root of a cubed is a. 1 factor of a gets factored out. The remainder of 1 tells us that we have a factor of a left over. That's because rewriting a to the fourth as a cubed times a, that single factor of a under the cube radical gets left behind. And that's why we just think about the shorthand idea of working with the exponents. Exponent of 4, root of 3, 4 divided by 3 is 1 with the remainder of 1. 1 factor gets pulled out, remainder of 1 indicates 1 factor of a remains under the cube root radical. To clean this up, simplify this out, cube root of 27 is in fact 3. Taking this whole factor of a and commuting it, just moving it and switching it with the cube root of 2. And now we have here the cube root of 2 multiply the cube root of a. We cannot further factor. We've already taken care of those two. These here, we cannot further simplify those down. So here we will further simplify by not having 2 radicals in our expression, but rather 1 radical. Product rule says here cube root of 2 multiply cube root of a. We can rewrite as cube root of 2a. That's our simplified expression for number 51. We see here for number 51. We started with a fraction under the radical. Step 1 said we can't have that for a simplified radical expression. So we used the quotient rule to break it apart for the numerator and denominator. That second step said we cannot have a denominator with a radical. Right now, we are dealing with a denominator with a radical. In our denominator, we have the cube root of b to the 9th power. Exponent of 9, root of 3. 9 divided by 3 is 3 with a remainder of 0. This means 3 factors of b get pulled outside of the radical. The remainder of 0 indicates that there are 0 factors of b left under the radical. So what does that also tell us? B to the 9th power is a perfect cube. Under the cube root, b to the 9th power becomes b cubed, because if you were to cube b to the 3rd power, b to the 3rd power cubed, our power to a power rule, chapter 5, section 1, 3 times 3 is 9. Thus, because you cube b cubed in order to get b to the 9th power, the cube root of b to the 9th is b cubed, giving us our simplified radical expression here of 3a. And again, if you want to write this in terms of a radical expression, write it as the fraction 3a over b cubed multiply the cube root of 2a, where our new radicand is 2 times a.